in the last class we talked about using the angular momentum principle to look at the dynamics of rigid bodies in motion. So, if you look at the other way, instead of using the angular momentum principle basis behind using the kinetic diagram. So, this diagram essentially, if you look at a rigid body that is subject to its weight and a bunch of other forces acting on it, the kinetic diagram is essentially the resultant, it expresses the resultant of these forces and moments. So, if I have this body subjected to its weight and other forces, say F1, F2 dot dot Fn up to Fn, then the resultant of those is equal to moment about the center of mass, a couple AIC equal to IC alpha, and m times the acceleration of the center of mass of the body. So, this is basically applying these Newton-Euler equations to this. So, this diagram is useful if you want to compute moments about points other than the center of mass, okay, because you will. So, take for example, in our case where we had the gymnast pivoting about the bar like that. So, if this was the free body diagram, you had only, we were looking at the effect of gravity on the motion of the gymnast. Okay. So, when you look at, in this case for instance, O is a convenient point to take moments about, because then you can eliminate the two unknowns in the equation. Okay. And so, if I use, so the kinetic diagram for this is this, right. So, I have it subjected to mg and the joint forces J r and J theta, and the kinetic diagram is just this rod subjected to IC alpha and MAC. Okay. Now, I know the acceleration of the center of mass, I also know the moment of inertia about the center of mass. It is a uniformly distributed rod. So, I use m into the length square by 12, the length here is 12. Now, if I want to compute moments about point O, so in this diagram I have moments about point O, this is equal to, on the right hand side I will have IC alpha, which is a free couple, okay, plus this. So, if I denote the location of the center of mass as RC, RC is say RC along ER. Okay. So, I have the moment of this equal to RC ER cross M AC. Here RC is nothing but RC is L, right, I took the length as 2L. So, it is just LER, the location of the center of mass. So, now I can say this is equal to IC alpha plus alpha is theta double dot. So, let me go back to that notation. Theta double dot plus LER cross M AC is L theta double dot E theta minus L theta dot square ER. So, the radial component obviously will not contribute to the moment, which you will see, because the product of ER cross ER will go to 0. Okay. So, it is the same thing as saying the radial contribution does not contribute to the moment about O. So, I get IC is ml square by 3 theta double dot plus I get ml square theta double dot from this product. The only thing that remains is ml square theta double dot. So, this is equal to 4 by 3 ml square theta double dot. Now, let me look at this. So, if I look at this term, right, ml square by 3 plus ml square. Okay, let me just look at this term. ml square by 3 is what I computed to be IC. Okay. Now, I have this mass m at located at L square. Okay. By the parallel axis theorem, right, the moment of inertia about O equals moment of inertia about C plus m L square. Okay. So, that is what this is giving me. So, I am getting from this, I am getting sigma m naught equal to I naught alpha, but this is valid only when O is a fixed point in the body. Okay. So, that is why it is always better to use the kinetic diagram, because if it was some point which was not fixed, then this relation is not likely to hold. Okay. So, in this case it holds, but there are other instances that we will see later where this will not hold. So, it is always better to use the kinetic diagram or start from the angular momentum principle rather than using this formula directly. Okay. So, that is something I wanted to alert you to. So, this is the from the parallel axis theorem. So, you can see that they are equivalent. Okay. So, now we looked at the rod as a distributed mass. If you simplify it to be a concentrated mass, okay, the center of mass will remain the same. Okay. So, your sigma f equal to m a, the kinematics remain the same. Okay. They are not influenced by the so, the kinematics stay the same because the location of the center of mass remains the same. What will change is your moment equation, because now your I naught in this case will be, so this is m at a distance of L square. So, your I naught will be m L square. In the previous case with a uniformly distributed mass, I naught was 4 by 3 ml square, we just saw that. Okay. So, if you use the concentrated mass approach, you are actually in this case underestimating the moment of inertia. Actual moment of inertia is higher than when using a model with a concentrated mass in this case. Okay. So, that is the trade off here. So, you should be aware of, when you use a particular model, what may be the limitations of that model. So, otherwise the analysis of this is the same and I am not going to go through it, but just to show you that if you make this kind of an assumption, because a point mass assumption is simpler than doing an integration, right. So, of course, for a uniform rod we all already know the formula. So, it does not really make a big difference, but in other cases you would have this is the compromise you make. The estimation of your moment of inertia would be different. Okay. Now, we will look at another interesting case. Okay. So, this was, we assumed that the athlete is applying whatever internal moments are necessary to keep the body straight. Okay. Suppose you want to figure out what exactly, so an obvious thing would be, okay, you have an upper body and you have a lower body pivoted at the pelvis, right. So, the obvious extension would be to look at, if I want to compute what kind of a moment the back or abdominal muscles have to exert in order to keep the body straight. Okay. How do I do that? Okay. So, we can start off with a simple 2 rod model. So, where I say that this is modeled as 2 rods with a hinge joint. Okay. And I want to first know, okay, if it just acts, suppose the person is let go from this horizontal position, okay, under the action of gravity, what is going to happen to these 2 rods? Will they tend to rotate with the same angular accelerations, or what is going to happen? Okay. So, we want to evaluate that, because that will then help me determine what kind of internal muscle moments I will have to apply in order to keep the body straight. So, let us look at this case. So, we want to assess the loads carried by the okay, just for simplicity this time I will take the mass as 2m, because it is easier to analyze. I have 2 rods, muscles of mass 2m, when let go from a horizontal position. So, the gymnast swings down, keeping her body aligned, but first we want to see, because we want to evaluate the loads exerted by the back or abdominal muscles, we model it as 2 rods connected by a hinge. Okay. We just want to see, okay, what is going to happen if you could not apply a moment in that region, how is this system going to move? Okay. Two rods, let us say O, A and B, OA and AB connected to, so let us say each has a length L and a mass M by a hinge at point A. So, we want to first answer the question, when the 2 rods are let go from rest in the horizontal configuration, will they begin to rotate as one solid body? intuitively you can say no. Okay, but if they did rotate as one solid body, then how would you know that they rotate as one solid body? Their angular accelerations would be the same. Okay, if we get different angular accelerations for the two rods, that means they are not rotating together as one solid body. And then if we want to make it rotate together as one solid body, give it a single angular acceleration, we have to apply moments. Okay. So, what muscles? So, these are the questions. What muscles? Probably a combination of the back and abdominal muscles must the gymnast contract to remain straight. So, I will tell you some of these problems are adapted from this. I will give you a list of references that I use for this. Many of these problems are adapted from the dynamics problems are adapted from Aidan Tozeren is the author. I think it is Dynamics of the Human Body. I will give you the correct, I will give you a list of references or if you look at your syllabus actually you have these books listed, but in this book for this problem they have it where the gymnast has their feet in the rings and then moves down with their arms stretched forward. Okay. So, let us compute the angular accelerations of OA and OB. So, it is released from rest . If this is theta 1, this is theta 2, but I am going to, for simplicity we now know how things are going to move, we know what the accelerations etc. are. So, I will not go through the whole formulation with r e r and e theta and all that. So, I will directly write it for this horizontal case, okay, since we know that we are looking at this particular configuration at as soon as they are let go, how is it going to move. So, at that instant we are interested. So, I will just go ahead and formulate it accordingly. So, since the rods are released from rest, theta 1 dot equal to omega 1 equal to 0 and I will designate theta 2 dot as, just for simplicity, as 0. Okay. Both are released from rest. So, omega 1 equal to omega 2 equal to 0. Now, let me call the center of mass. So, if I look at this rod OA, I will call the center of mass as D. Okay. So, I have the acceleration of D, I can write it directly. What would be the acceleration of D? In terms of alpha, it is just alpha 1 into this distance is L by 2 along J in the horizontal configuration. So, we are analyzing it released when it is released from rest at theta 1 equal to theta 2 equal to pi by 2 at that particular configuration. My alpha 1 and alpha 2 are what I am interested in finding. Okay. Now, I have, when you look at interconnected bodies, okay, I can, if I take E as the center of mass of the second rod, rod AB, okay, that is another acceleration I am interested in. I want to find the acceleration of E. Okay, so for a system in a rigid body, if I have 2 points in a rigid body, say P and Q. Okay. I can, if I know the velocity of P, I can write the velocity of Q as the velocity of P plus omega cross r of Q relative to P, right. Similarly, I can write the acceleration of Q as the acceleration of P plus alpha cross this plus omega cross the relative velocity vector. So, in planar motion this all simplifies, right. This will be alpha times RQP in the tangential direction, this will be in the radial direction. So, essentially it is because if you look at 2 points in the rigid body, how can Q move relative to P? See, if when I say this is a rigid body, it means the distance between points P and Q does not change as the body moves. So, there can be no velocity component of Q in the line joining P and Q. The only way Q can move relative to P is along a circle centered at P. So, that is where this comes. This is your the circular motion that is happening about the point P, and similarly the acceleration is also due to that. You have the centripetal component and then you have the tangential component. Okay, so, that is the basis for this equation, because Q can only move along a circular path because the distance between P and Q do not change, because of the assumption we have made that this is a rigid body. Why is the assumption of a rigid body valid in most cases? Because if the deformations are small relative to the motions that the body undergoes, then the assumption that this is a rigid body is a valid assumption. Okay. So, in this case now, if I look at this point E lies on AB. Okay. A also lies on OA. Okay. So, I can write the velocity of acceleration of E as the acceleration of A, okay, plus the relative acceleration of E with respect to A. And this is equal to acceleration of A is nothing but alpha 1 into L along J, because it is moving about this fixed pivot O, and then acceleration of E relative to A, because omega I am assuming is 0 at that particular instant. So, there is no radial component. Again this component is also the it is alpha 2 into L by 2 J. So, these are the two accelerations of the centers of mass of the two links. Okay. Now, let me look at the free body diagram. So, I have O, A, and I have point D. So, I have mg acting at point D. If I draw the free body diagram, I have the reactions, let me call it OX, OY at the pin joint. It cannot support a moment, it can only prevent horizontal and vertical displacements, and then A is also a pin joint. Okay. So, I can say the reactions at A are Ax and Ay. So, this becomes my free body diagram for OA. And so, I can apply sigma Fx equal to Max, sigma Fy equal to May, and because O is a fixed point, I can also apply sigma m naught equals I naught into alpha 1. Okay. So, I have Ox plus Ax. Please make sure you are also working it out with me, so that if I make a mistake you can fix that. This is equal to minus m omega 1 square into L by 2, but omega 1 is 0, right. It is the radial component. Ox, there is no radial component here because I have assumed it is starting from rest, that is equal to 0. Then I have Oy minus mg plus Ay equal to m into alpha 1 L by 2, and sigma m naught equal to I naught alpha 1, which gives me, if I take moments about O, because then I eliminate these two, Ax will also not have a moment about O. So, my only unknown will be Ay. Okay. So, then I get minus mg into L by 2, I am assuming counterclockwise positive. So, minus mg into L by 2 plus Ay into L equal to, what would be the moment of inertia of this rod about O? It will be ml square by 3 into alpha 1. Okay. So, ml square by 3 is the moment of inertia of rod OA about fixed point O. So, if I had the rod mass lumped at the center, my moment of inertia would just be m into L by 2 whole square, ml square by 4, which again is an underestimation. It is actually ml square by 3. So, now I draw the free body of A B, and let us say its center of mass is at E. So, I have mg. Now, my Ax and Ay will be in the direction opposite to what I took earlier, right. So, I have Ax, so I have mg, I have Ax now in this direction and Ay in this direction, and B is a free end. So, there are no reactions there. In this case, I know Ay now from the previous equation, right. So, if I go back here, I can, no, I know Ay in terms of alpha 1, okay. I do not know alpha 1 yet. So, I could express both in terms of that. I can apply about the center of mass, it always applies the moment equation. So, I could say sigma me equal to I e alpha 2, this is perfectly valid, okay. And I can then from my sigma fx sigma fy I get Ax equal to 0, because there is no radial acceleration, because omega 2 is 0 at this instant. Then I can write minus Ay minus mg, sorry, yeah, minus mg equal to m A e along the y direction, which is again the acceleration of E is m into alpha 2 L by 2 plus alpha 1 L. I found that in the previous alpha 1 L plus alpha 2 L by 2, that is the acceleration of AE. If I apply this for the third equation, I get AY into L by 2, okay, mg, no moment due to mg, no moment due to AX, is equal to, now it is about the center of mass. So, the moment of inertia is ml square by 12 times alpha 2. So, I can say therefore, AY equal to, I can cancel this out, I get ml by 6 alpha 2. This is AY. So, essentially in these equations I have, so for each free body I have 3 equations. No, AY causes a moment about about E in a counterclockwise manner, which is positive. Okay, I am taking counterclockwise positive. So, I basically, my unknowns are, I have 6 unknowns that I can solve for. Each rigid body has 3 equations. The 6 unknowns I solve for are OX, OY, AX, AY, alpha 1 and alpha 2. So, if you solve for these, you get, please do that, I get alpha 1 equal to minus 9g by 7l, alpha 2 equal to three g by 7l. An easy way to solve for alpha 2 would be to take the moment about, would that do it? Anyway, you can solve these are not very hard to solve, they are fairly simple algebraic equations, but this is what you get. What this tells you is that, so they try to rotate in opposite directions with unequal accelerations. So, that means you cannot just, if you stay completely relaxed, your upper body and your lower body will tend to move in different directions. If you are let go from rest in that position, you are not going to be able to stay straight, because if you want to stay straight, it means you are making the 2 angular accelerations equal. Okay, you are rotating as one single body, and that is not going to be possible without some muscular effort. Let us see if the body remains straight from the beginning, what will be the angular acceleration. Okay. So, if the body remains then you have a single rod of length 2L, mass 2 mg. Okay. And I can just compute this as, if I take moments about O, sigma m naught equal to I naught alpha, if alpha is the angular acceleration with which it rotates. So, then I get minus 2 mgl, this is O, equals, what is my I naught? Mass ml square by 3, right. Length is 2L by 3 alpha. Therefore, alpha is minus 3g by 4L in this case. Now, let me look at, I want to find out what is the moment that has to be applied in order to achieve this. So, let us say this is O, this is A, this is E. I have 2 mg acting here. What would be the acceleration of the point E? What would be the acceleration of point E? It is just rotating about this fixed alpha into 3L by 2, because that is the distance to point E, alpha into 3L by 2. Now, what is alpha? Minus 3 by 4 g by L into 3L by 2, which gives me minus 9 by 8 g. That is the acceleration of E. This is in the negative y direction. Okay. Now, let me draw the free body diagram of AB, because this is where I want to see what is happening. I have mg acting at the point E. Okay. Let me say I have an Ax, Ay, but now I am also applying some moment at, let me assume it is the abdominal muscles applying that moment. So, instead of actually looking at insertions and all that, let me just compute the net moment that has to be applied at that joint in order to, because muscles essentially apply moments. Okay. And muscles, you may not have a single muscle acting. In the previous studies we looked at, we made the assumption that one muscle is acting and then we computed the muscle force, but essentially the muscle is applying a moment about the joint. Okay. So, you will see that in a lot of biomechanical analysis, because a joint is not acted on by just one muscle, it is usually, it is always acted on by pairs of muscles. You have the agonist and the antagonist acting at any joint. So, you will talk about net joint moments. So, the agonist applies a moment, the antagonist applies a moment, and the net moment will probably be in the direction of the agonist moment. Okay. So, that is how we look at. So, here we will just look at the analysis, we will just compute a moment that is being applied at that joint. So, now if you look at this, here is a case where the kinetic diagram becomes important. Okay. So, let us say if I want to compute the moment about A, okay, this will be, so the kinetic diagram for this would be, I have at the center of mass, I have M A E, okay, I am just assuming some arbitrary direction, and I have I E alpha, moment of inertia about E, because E is the center of mass for this rod. This is A, this is B. E is the COM of this rod. So, I have sigma MA equal to IE alpha, okay, from the plus R of E, R of E relative to A cross M A E. The moment of this force about A. Now, the problem with directly applying, so in the case of A being a fixed point, okay, the acceleration of E is straightforward. It gives you R alpha, right, and so M R square, you get that term which is the same as the moment of inertia by the parallel axis theorem moving. In the case of this, the acceleration of E comes from the movement from O, right. It is the movement from O that is causing the acceleration of E. It is not going to be AE times alpha, you have already seen that. Okay. It is not L by 2 into alpha, it is 3L by 2 into alpha here. Okay. So, that is where it is important that you use the kinetic diagram to write this equation rather than just writing it as sigma ma equal to Ia alpha, that would just be wrong. Okay. So, if you do this, you get ml square by 12 about E alpha, alpha is minus 3g by 4L plus L by 2 along I, in this case cross minus 9 by 8 mg along J, that is my m into AE. So, this is equal to minus mgl by 16 minus 9 mgl by 16, that is equal to minus 5 by 8 mgl. So, although this example is from that book, in the book there is an error in the computation of the dynamics. So, your values for alpha and these will not match in that, okay, just to warn you, but the problem is from there. So, this is minus 5 by 8 mgl, and then this is equal to from this free body diagram, okay, sigma ma is equal to minus mg L by 2 plus m a b. Okay. So, using these two, and this is equal to from here minus 5 by 8 mgl. So, I get m a b equal to minus 5 by 8 mgl plus half mgl, I get it as minus mgl by 8. So, that means the net moment is a clockwise moment. So, which muscles are dominating? Which muscles are applying the net moment? The abdominals or the back muscles? The net muscle is clockwise. You have the body like this, your abdominal muscles are working. So, you have to contract your abdominal muscles to apply this net moment, because your back muscles will also be contracting. So, overall you have to apply a net moment of mgl by 8 in order to keep your body straight while moving down. Okay. So, this is the net effect. So, that means the abdominal muscles are that is what this tells you. Okay. So, this is actually the net effect of the agonist and antagonist muscles. In this case, the antagonists are the back muscles, and there will be other. See, it is very difficult to isolate and say this muscle is, because you have other, you have ligaments, you have so much soft tissue around in the body. The best you can do is kind of compute these net moments. You need more sophisticated models which model say the individual ligaments and muscles and all that, but those are very hard to solve. You have to use some kind of optimization techniques to solve those models. They are called musculoskeletal models. It tells you how the different muscles behave and all that. but they are computationally very intensive. Okay. But this kind of a simple analysis can give you insights into what is happening here. Okay. So, this is how you do a more complex problem in rotational motion. So, if you are interested in the interface moments, then you have to ensure that that is modeled as a joint, so that then you can compute the, using that free body you can compute the moments at that interface at the joint. Okay. All right, we will continue in the next class.